Hello everyone. In this lecture, we will look at the simulation of a 16-bit full adder circuit using Logisim software. Let us look at the implementation of 16-bit full adder circuit. So we will begin with 1-bit addition with carry from the previous stage. So it forms a full adder circuit. Here carry also is included. Then we will get the truth table. Once we get the truth table, we will build the logic expression from the truth table. And then we will minimize the logic expression using Boolean algebra. And then we build the digital circuit. In fact, this is the general procedure for us to build digital circuits. You start with the truth table, get the logic expression out of that. From logic expression, we minimize the logic expression using Boolean algebra so that the number of logic gates are reduced, and then we build the digital circuit. Well, the truth table for 3-bit addition looks like this. So if I am having two inputs A and B, and if both A and B are zeros, and if there is no carry from the previous stage, then sum is 0 and the carry out is 0. Now for the same inputs which are 0 and 0, assume that if there is a carry from the previous stage, then sum will be equal to 1 and carry out in this addition operation will be 0. For example, if A is 0 and B is 1 and carry input is 0, if there is no carry, now the sum by adding these three bits is equal to 1 and C out is 0. You can proceed further with the different combinations and you can get the truth table for 3-bit addition that includes carry. Alright. Our next objective is to get the expressions for sum as well as carry output, from where we can build the logic circuits. Now, wherever we get sum as logic 1, pick those corresponding input term. For example, for this particular logic high output, the input combinations were A is 0, B is 0 and carry input is 1. The zeros are represented by bar and ones are represented as they are. So for this particular high output, the corresponding inputs are A bar, B bar and C in. That's what I have put here. Similarly, if you write for the other logic high outputs for sum, so this is A bar, B, C in bar. That's what I have written here. A bar, B, C in bar for corresponding this output. For this logic high output, the corresponding inputs are A, B bar, C in bar. That's what I am writing. That's the third term. And for the last term, it is A, B, C in. Similarly, we have to write another expression for carry output. So for this particular output, the input variables are A bar, B, C in. That is the first term. And the second term is A, B bar, C in. Third term is A, B, C in bar. And the last term is A, B, C in. Alright. So this is the logical expression for sum and carry respectively. Suppose if we build a circuit straightforward from here, it will have a large number of gates. So more number of gates means more number of transistors, more is the chip area. Well, in order to reduce chip size, we need to minimize these logic expressions using Boolean algebra. I am not showing all the procedure here. If you minimize, the expression for sum reduces to A XOR B XOR C in. Similarly, C out is A dot B plus A XOR B dot C in. Now, these particular logical expressions can be built using a circuit. So, it has got three inputs A, B and C in, and there is sum and carry out. So, this circuit represents 1 bit full adder. So, this is a 1 bit full adder circuit, and this circuit includes carry input. Suppose if we were to represent this like a single bit full adder circuit, you can represent it like a block which is having three inputs A, B and carry input from the previous stage and sum and C out as the output. Why are we representing with a block? The reason is this particular circuit is having 5 gates for implementing just 1 bit full adder circuit. For example, if I were to implement 4-bit full adder circuit, I require 4 5s 20 gates, which is really difficult to put in the Logisim software. So what I am doing is, I am representing this full circuit with 3 inputs and 2 outputs as a block. Right. Now I will use this block as a basic building block for constructing 4-bit full adder circuit. So here I am using 1, 2, 3, 4 bits. So starting from LSB, then second bit, third bit and MSB. Right. So each block has input A, input B and carry from the previous stage. So I am giving 4 bit inputs for A as well as B, and I will get 4 bit outputs for sum, and if at all there is any carry, there is a provision for carry out. So here each block is a 1 bit full adder circuit. The carry from the first stage goes as the input to the second stage, and the carry from the second stage goes as the input to the third stage, and the carry from the third stage will goes as the input to the fourth stage. So this is a 4-bit full adder circuit. Now this 4-bit full adder circuit, again I am going to represent like a single block. Now here each block is representing a 4-bit full adder circuit. Now if I use two 4-bit full adder circuits, I will be able to make an 8-bit full adder circuit. Here 4-bit full adder circuit is basic building block. Alright, this also has provision for carry input. Right, I am having the input A, which is 4 bits in length, which starts from 0 to 3. So MSB till 4th bit, which is represented by 3. If I represent them like data, it is D0, D1, D2, D3. 4 bits for input A, then 4 bits for input B. I add these 4 bits from the two inputs A and B, and I generate sum here. If there is any carry, I forward it to the next stage. Here I am adding the bits from 4 to 7. Again this is 4 bits in length. Here I am getting input from A, here I am getting input from B, which are 4 bits in length. This is how a 8-bit full adder circuit is implemented using two 4-bit full adder circuits. So here each block represents one 4-bit full adder circuit. Now if I were to construct a 16-bit full adder circuit, what I will do is, I will take 4 4-bit full adder circuits. The carry out from the first stage is given as the carry in for the next stage, and here I am having bits from 0 to 3, 4 to 7, 8 to 11, 12 to 15. So from 0 to 15, here I am adding. Therefore, this is a 16-bit full adder circuit. Alright, let us look at the implementation of this particular circuit. Assume that I am already having a 1-bit full adder circuit. Well, let me add pins for this particular circuit. Right, the input pin, this is for carry. So please don't connect directly there, rather you place it little bit away and connect it with wires. Right, now we will connect output pins. Now the next important step is we will label each input. So this is carry. Select this and you should be able to see the option to enter a particular name in the label column. Click here. This is C in. Right. So you can see C in here. Let us make it bold. Click on label font and click on bold to make the particular entry bold. The second one is input A. Again I am making this bold. I am labeling for B input. Make it bold. This is sum. So I am labeling it as SUM. Making it bold. This is carry. C out. So doing so will help us in identifying which input is what when we are making a block. Let us save this particular circuit. Save. 16-bit. Okay, let's call it full adder circuit. Now the name here changes as full adder circuit. Now go to project, add circuit. Right. So the next circuit what we wanted to make is 4-bit full adder. So I will make it 4-bit full adder. Right. Now select this. You should be able to place a block like this. Now if you place mouse here, you can see what is the input. This is C in, this is A, this is B, this is sum, and this is C out. So this particular block represents 1-bit full adder circuit. Now if I want to make a 4-bit full adder circuit, I need to copy 4 such circuits. Just select on main and you should be able to select a block. Select on main. Now first thing is from all the C outs you connect to C in of the next stage. This is C out. Alright. Now input A is 4 bits in length. So let us connect this for input A, for B. Alright. So let us use a splitter. Go to wiring. There you find a splitter. So make the fan out to be equal to 4. Now start connecting these wires. Alright. So now let us connect here. It says incompatible widths. So we have used a splitter which is 4 bits in length, but the input is only 1 bit in length. So select here and make data bits equal to 4. Right, again we will label here, it is A4. Let me call it as A4 to represent 4 bits. Right, let us make it bold. Similarly, we will use one more splitter. So make fan out equal to 4. Connect. So it tells incompatible widths. This is for B input. So select this, make data bits equal to 4. Right. Let me label it as B4. It is 4 bits in length. So I'll make it bold. Alright. Now let us connect for carry input. Alright. So at the output also we will get carry as well as sum. Sum is 4 bits in length. So we will paste here. So this is for sum. Make it bold. Now we require a splitter again here. So make fan out 4. Now let us turn it the other side. It tells incompatible width. So sum we have to make 4 bits in length. Now let us start connecting all the outputs for sum. Now this one for carry out. Alright, this completes 4-bit full adder circuit. This is carry in, this is carry out. The input A with 4 bits in length, input B with 4 bits in length. Now let us perform an addition. So let us make all these inputs, go to poking pin, make all ones and check whether sum is equal to all ones. Right. Now we will make B input also equal to 1. Now for this particular addition, you get sum equal to 1, 1, 1, 0, and there is carry for this also, which is 1. Well, this circuit works fine. Alright. Now, if we were to make an 8-bit full adder circuit, we have to make this as one block. So again go to project, add circuit, 8-bit full adder if I were to make. If you click here, you will get sum, carry. This is for carry input. This is A4. This is B4. Alright. This block represents a 4-bit full adder circuit. If I were to make 8-bit full adder circuit, I need to have one more such block. So as usual, let us connect the carry out of first stage. So if you place mouse over there, you will be able to see what it is. Right. This is sum. This is carry out. Alright. Now let us complete the rest of the circuit. So I am connecting for the first one. It says incompatible bits. So we have to make this 4 bits. So this is for, let me label, this is A4, 4 bits in length, and this starts from 0 LSB to third. So if I call like D0, D1, D2, D3, these are the bits. Right, let me make it bold so that we can see it clearly. So this is for A. Now similarly, again incompatibility has arrived. Again it is incompatible bits. So we will make it 4 bits. Now let us label this. This is for B input, which is 4 bits in length, and the data bits are from LSB 0 to MSB 3. 0 to 3. Let's make it bold. Alright. Same things you can just copy and paste here instead of doing all the time. But labeling you have to do properly. So make them 4 bits. So here again this is corresponding to A input, which is 4 bits in length, but the bits are from 4 to 7. 4 to 7. Bits are from 4 to 7. Let us make them bold. For B input, So let us make it 4 bits. So label B4 from 4 to 7. Carry input. Now sum here is 4 bits in length. Sum here is 4 bits in length. So let me call S sum, which is 4 bits, and from 0 to 3. Make it bold. Now one more sum, make it 4 bits. So let me label this as 4 bits in length. Sum is 4 bits in length. Now it is from 4 to 7. Alright, now the carry is left, so we will add carry, which is 1 bit in length. Alright, so let us check whether this works or not. For all zeros, we are getting zeros. So let us make all of them ones. So a carry has come. Right, so this is fine. Now this also we will make all zeros into ones. Right, so this is the sum. So it is, sum is 8 bits in length and there is carry. So you have to read like this: 1 1 1 1 1 1 1 0. Alright, so this is LSB and this is MSB, and this particular addition has generated a carry of 1. Alright, from two 4-bit full adder circuits, we could generate an 8-bit full adder circuit. So the input is 8 bits in length, the output also is 8 bits in length. If you are having a carry, there is one more extra bit for that. Now if we were to make this a 16-bit full adder circuit, either you take 4 4-bit full adder circuits or 2 8-bit full adder circuits. So again go to project, add circuit, 16-bit. Alright. So this is carry in. This is, here you have to give inputs, 4-bit input from 0 to 3. Here it is B4 from 0 to 3. This is A4 from bits 4 to 7. This is B4 bits from 4 to 7. This is carry input, and if you look here, this is sum, which is 0 to 3. Here it is sum, which is from 4 to 7. Here you will get carry. Alright, so copy this and paste. So connect appropriately. The carries are connected. Like how we have connected, the same way we have to connect. This is for carry input. This is for carry output. Alright. Now all other inputs. Incompatible. So this we have to make 4 bits in length. This is for 0 to 3 for input A. So make this as 4 bits. So this is for input B and bits are from 0 to 3. So make this 4 bits. This is for A input and bits are from 4 to 7. Similarly, you have to connect here also. This is sum. Make it 4 bits. Right. This completes a 16-bit full add circuit. Of course, this is left. Alright. So this is input A from 0 to 3, input A from 4 to 7, then again this is input A from 8 to 8, 9, 10, 11, then this is input A from bits 12 to 15. Alright, let me label these things for timing. So this is A4 0 to 3, this is A4 z 4 to 7, and this is input A, 4 bits in length, from 8 to 11, bold, and this is input A, 4 bits in length, which is 12 to 15 bits. Alright, similarly this is for B. Now you can poke and make all of them once and see what will happen. All output should become 1 with a carry of 1. Well, so the circuit works fine. Now if you were to convert it to a 32-bit adder, you can make this a block and you can continue further. So this is how you can implement a 16-bit full adder circuit starting from here. So go from 1-bit full adder circuit, then from there make each block 4-bit full adder circuit, then use two 4-bit full adder circuits to make 8-bit full adder circuit, use 4 4-bit full adder circuits to get 16-bit full adder circuit, or two 8-bit full adder circuits to get full adder circuit. Thank you.